Welcome to the course on polymer assisted abrasive finishing processes. Today we are going to have an important class where we understand what is the practical application of this particular course. How this polymer assisted abrasive finishing processes, especially in terms of abrasive flow finishing process, where you will use polymer assisted or polymer rheological abrasive fluids. So moreover, you also see some of the other applications also, but I am going to concentrate mostly on bioimplants. See, importance of finishing, you should also know what is the importance of finishing. It will improve the fatigue life. If the surface roughness is less, that means that your contact area or bearing area will be high. Assume that figure 1 and figure 2 if you take, what will happen? Bearing area for figure 2 will be much high compared to figure 1. At the same time, crack formation. Whenever you have the crack formation because of the surface roughness, there may be always a crack formation will takes place wherever the valleys are there. At the same time, it can eliminate the vibration. Means whenever you have the surface is too rough, figure 1, assume that my surface is too rough, and on top of it if you have any load, if you are putting, what will happen? It will be on the only peaks. After some time, what will happen? These peaks will shear off and it will give some eccentricity. Assume that this is the practical application is in terms of a shaft that is there in a bore, and this surface is very rough like this, and your shaft is mounting on this one. So what will happen is after some rotations, this shaft will fail because of the rough peaks will shear off. Then vibration will come into existence. Then less susceptible to corrosion. That means that if you surface is like this and fluid flows on top of it, what will happen? The fluid can stay more in quantity whenever the surface roughness is high in this one compared to the low surface roughness. So the corrosion will be also high. To provide sharpness to the cutting tools, at the same time you can also give good aesthetic appeal. As you can see here, the knee implant, which we are going to talk mostly about the knee implants and hip implants as well as cardiovascular applications and other things. If you see the knee implant 1 and knee implant 2, what is happening here is, if you are going to place the knee implant 1, the surface roughness is too high, surface roughness may obstruct the body fluids. Assume that the body fluids flows on it. What will happen? It will obstruct the flow. At the same time, if you have the flow on this one, there may be obstruction, but obstruction compared to the unfinished surface, it will be less. So the body fluids easily flows and body fluids won't stay in the surface valleys and corrosion will not take place. And the life of this knee implant will be enormous. Now we look forward in the upcoming slides how the nano surface finish improves the biomedical devices. Polymer assisted abrasive medium for macro to micro features. In this one, what are the few geometries that we are going to do? Practically speaking, this is not exactly what we are going to finish the knee implants or hip implants or cardiovascular applications or something, but the preliminary study, preliminary experimentation that we have done at our laboratory is shown here so that you can understand. If my workpiece is bio-stainless steel or surgical steel, if you want to finish these tubes, you can go for high viscous medium. As the geometries are going down or the geometries are reducing, what will happen? You have to use the low viscous medium. So the medium development itself is a very challenging task because you have to play with minimum 15 to 20 ingredients. The basic problem comes like stickiness, self-deformability, self-upgrading ability, and moreover the sedimentation problems. These are all things are there. So you have to choose obviously a good base polymer, rheological additives. Which rheological additives that you are choosing will decide what is your viscosity, at the same time your stickiness to the surface. If the stickiness is very high, what will happen? It will stick onto the surface and the other layers of the medium will flow on top of it. So, in respective of how much sticking is there, it just simply flows on the surface rather than abrading the surface. In that circumstances, what the biggest problem is, even though you are going for 100 cycles, 200 cycles, n number of cycles, the finishing action will be much less. Whenever you take the implant out and you can cross check, the surface finish may not be improved. For that purpose, you should have good abrasive particles, chemical compatibility and other physical compatibility between all the ingredients should be good. Suppose for example, you are using a silicone based with carbon based compositions. Normally the compatibility will not be very good. So, you have to choose carbon based means carbon based. If you want to choose completely silicone based means silicone based. So, there are some terminologies and other things which covers in the medium development. For example, if you want to go through the medium and its rheological characteristics and other things, it itself is a very big course. So, just I am giving you some of the glimpse. If at all I want to go for a micro slot, if at all I want to go for a tube, what are the various properties and other things. So, these are the rheological properties which I have already discussed when I am teaching about the abrasive flow finishing process. So, these are the same thing, but the medium compositions are slightly different. But the physics, linear viscoelastic region, creep recovery, elastic region, viscoelastic region, elastic recovery and all these things are approximately same. And what is here shown is, one is for macro applications, another mediums are for micro applications like micro hole, micro slot and other things. Now, you will understand in the upcoming slides why we want to finish the macro features and why we want to finish macro features. So, first we start with macro features, big features like a stainless steel tube or surgical stainless steel tube. These surgical stainless steel tubes are mostly important in various surgical aspects and other things. If you see the initial surface roughness, normally this is a boring surface. The boring will be done inside the workpiece and the surface approximately looks like the turning process only, and then you do the polishing process using the medium that is given. So, you will get the initial profile and final profile. How the finishing will takes place and other things, it is same as abrasive flow finishing process. In this particular class, just I am going to explain you the applications, because you should know why you are studying this particular course. If you can understand why you are studying this particular course, then you will get the essence of this particular course. So, initial boring marks, you can see these are the dominating initial boring marks are there. Similarly, the same 3D graph is there as well as 2D graph is there. This surface has to be finished. You have a viscoelastic medium where viscous component is there, elastic component is there. You have a abrasive particle that is supported by your polymers, and polymer will put your radial force here and axial force and axial velocity here, and shearing will takes place. Assume that my abrasive is there, it will go and shear the surfaces and it will give me a good surface like this. And at the same time, this particular paper is already published. If somebody wants to know about this details and other things, they can go through. This is a paper published by Dr. Sachin Singh and Dr. Ravi Shankar from IIT Guwahati. So, more details can be known from that particular paper. At the same time, you can see here, however, after polishing, see that means that this particular is refers to this one, or this is refers to this one, and this particular surface is refers to this one, and this is refers to this one. That is what is the importance of finishing. However, Here I am not talking about much parameters and other things, because macro is not that much complicated. That's why I will talk about some of the physics of finishing in terms of micro holes as well as micro slots, so that you can understand. Because in abrasive flow finishing already I conveyed you regarding the macro features and its finishing. So in this particular class I will concentrate slightly more in micro features. First we start with macro features, then we will go to micro features, and this is particular study is conducted at IIT Kanpur and CMTI Bangalore. So some of the researchers is also done by Kennametal Extrude Hone. Okay, this is done at CMTI Bangalore and Kennametal Extrude Hone. Not only abrasive flow finishing process can do the polishing, it can also done by MRF process and other processes also. This is the knee implant initial surface, which is too rough. That's why IATK word is not that much visible on this one. How to polish the knee implant? So for that purpose we can use the abrasive flow finishing process, wherein you have to play with polymer rheological abrasive medium and you have to design a special type of tooling. This picture is familiar to you because you are going through the abrasive flow finishing process, wherein you have abrasive medium is there, workpiece fixture is there. This is the area where you are going to fix your fixture. So your fixture has male and female part, wherein your knee implant is mounted, and it can be finished by using a polymer rheological abrasive medium. You can see this is a male part and this is a female part, so that this male part and female part can sit together and the polishing can be done. After putting this into this one, so you can also close with this one. So part 1, part 2, then you have these two combined will give rise to this, and when you place part 3, part 1 and 2 and 3 are placed to get the surface, and you can hold the workpiece intact, and the main purpose of tooling is to hold the knee implant in position to allow the medium across the surface of the finishing, so that the finishing can be taken place properly. Okay, you can see here how the medium is flowing and other things there, and the curvature is completely different from point to point. For that purpose, what you have to do is you have to measure the surface roughness at different levels. That's why the author has given at different phases he is going to measure the surface roughness value, and you can see how the polymer abrasive medium is flowing on the knee implant. This is how the knee implant it works. This is how the polymer rheological abrasive medium flows across the surface to be finished on the knee implant, and the finishing can be taken place. You can see the surface, the initial surface roughness, which is considered in the normally area surface. It is approximately 182 nanometers. After finishing, it is 36.3 nanometers. You can see again on other side, because I said that it has a changing of curvature is there at many places, because of which you have to measure at different locations. That's why it is measured 2 locations here. So location 1 and location 2, initial and final surfaces, and at the same time it is also measured at different phases, phase 1, phase 2, phase 3, phase 4. In phase 2A is given here, and phase 4B also given the 3-dimensional surface, so that you can measure at different levels, or you can measure at different regions of the knee implant, and you can give what is the average value of the surface roughness on the knee implant. You can also see here the final RA with respect to angle or whatever is the angular and change in surface roughness. If you see at different angles, it is moving at the face, and you can also require the surface roughness at these surfaces, because this is the area where you have to have the relative motion and other things. So the medium which you have to prepare, it should have good amount of shear stress. At the same time, if you are going to put temperature, as you can see here, if you are going to increase the temperature, what will happen? The shear stress of the medium will decrease, then polishing efficiency will slightly reduces. Now we move on to the hip implant. Especially we deal here with the acetabular socket. Some people they may call it as acetabular cup, some people they call it as acetabular socket and other things. So in a hip implant, acetabular head as well as acetabular socket, both are to be properly polished, otherwise the relative motion will be not good for the patient. This is acetabular head, or normally it is made up of a ceramic material. At the same time, this is acetabular cup or acetabular socket also you can say. But in acetabular head, we mostly bother about the external surface. In acetabular socket, we bother about this internal surface roughness value, so that the contact will be proper. So normally the head will be machined first and then it can be polished. So the two important locations in a hip implant is acetabular head top portion as well as acetabular socket region. These are to be polished. Very simple mechanism is found here, and you just have a aluminum tool and you have a fixture to hold the acetabular socket. Normally we can design a simple wooden based fixture that can be placed on a milling machine, and milling cutter can be replaced by the tool that you can design according to your requirement. This tool looks very simple, but recent works we are doing our complicated things because we want the tool to be more viscoelastic in nature. So some of the recent works are unpublished, so we are not showing here. However, the same principle is followed there also. You can see the end milling cutter collet. So you can hold your tool here and you can hold the workpiece here. You can see here, assume that I am holding my workpiece here and my tool is here, and the tool will need to have the polymer viscoelastic medium. For that purpose, what we have done is we have taken sufficient amount of polymer rheological abrasive medium that is exclusively prepared with some of the advanced abrasive particles and polymer rheological additives, and we have done the finishing operation. So the initial surface roughness is measured. Normally initial roughness is approximately is 4.04 micrometers. This is measured using a non-contact interferometry based surface profilometer, and this is the surface roughness. Average surface roughness is approximately 4 micrometers. We want to finish the surface roughness of the bottom side of the acetabular socket. So this material itself is a very complicated material. This is material we have procured from ISC Bangalore, and this is a ternary composite where ceramics, polymers and bioceramics are involved in it. Now you can see the tool and the workpiece fixture and other things. The tool is here, the workpiece is in the fixture. Now workpiece is placed beneath the tool and it is filled with optimum amount of the medium that is already optimized its composition. Okay, simple medium is used here. However, the people can go for complex mediums and other things. The medium whatever here is a silicone based medium. Is just a simple medium where we have used very less amount of abrasive particles. However, this medium is not going to give very better results, but preliminary experimentation as per the analysis, just we want to check whether the finishing action is going on or not. For that we have done using the silicon based polymers along with the hybrid abrasive particles, and the surface roughness you can see here from 4 microns or 4.04 microns, the surface roughness is reduced to approximately 0.47 micrometers. That means that the surface is enormously improved, but the pits or some delamination is another basic problem here. That's why we need to go for the advanced polymers where you can make the polymer assisted abrasive medium. As I said, this is just a preliminary study where we can do or where we should understand that whether the process is working or not, that the tool is working or not. For that purpose, we have tested the surface roughness has enormously decreased, but this cannot be used directly into a practical application. However, the life of this particular component will be greatly enhanced because the surface roughness is drastically reduced or enormously reduced from 4 microns to 0.4 microns. Now, we move on to the micro components or micro features that are normally used in many biomedical applications. The first one is micro slots. These micro slots are finished using polymer assisted abrasive finishing processes where the medium is too low viscous. That means that as you have seen in the first slide or second slide that there is a different mediums are there, and these are the mediums. As your passages are small and small, what you have to do is you have to reduce the viscosity of a medium and you have to go for the fine to superfine abrasive particles. Then only these abrasive particles will pass through these narrow gaps. So, the applications of these micro slots can be used in coronary stents and so on, like micro filters and other applications. As you can see here, these are done using the laser beam machining and electric discharge machining. For example, if you see here, what is happening is this is done by a advanced machining process. Because of this, what will happen? You can see the parent material and metallurgically destroyed material around. This material will have enormous recast layer, heat affected zone and debris. As you can see here, a recast layer is there and debris is there. For example, if you are going to use this particular component in a biomedical applications, for example, drug eluting stents, what will happen? Your drug is going to elute from this position, and your drug is one type of chemical, and this will react with the debris that is there on the path through which it comes, and it may also loosen, and this debris may also cause lot of problems to your heart. If this enters, these are very hard materials and your heart or any other body parts are very soft tissues, and this will damage the human body. That's why you should be very careful in using these biomedical devices. Before that, you have to do the proper polishing so that you can remove the unwanted materials. How this is finished? The micro slots are there. These micro slots, the extrusion pressure, number of cycles, mass, weight percentage of abrasives and other things are there. But however, much details are not given here about the medium, because medium itself is very complicated. As I said, whenever you are moving towards liquid type of medium, what will happen is sedimentation problems will come, and these problems has to be overcome by choosing proper rheological additives into the medium. Okay, this is the fixture, this is the workpiece. This workpiece is placed in the fixture. You can place your workpiece here and you can extrude the medium through this one, so that the finishing action can be taken place and these micro slots can be finished. Now we will see some of the basic mechanism, because we have seen the mechanism for the macro applications in abrasive flow finishing process. Here we will see similar to that one in micro abrasive flow finishing process. So, this particular class not only covers your biomedical devices finishing, but also covers micro abrasive flow finishing also. Whatever you are seeing here, polymer assisted abrasive finishing of micro slots, and whatever you are going to see in micro holes in the next few slides, this is a part of micro abrasive flow finishing process. So, do not think that micro abrasive flow finishing process is a different process and this is different. Whenever you are finishing the micro features, then you can call it that particular process as micro abrasive flow finishing process also. You can see here the extrusion pressure. As the extrusion pressure increases, what will happen? Percentage change in RA gradually increases. That means as you increase the extrusion pressure, the holes that are fabricated using EDM process. So, in the EDM process, you take very thin sections in the die sinking EDM, and you can do the machining of these slots. Then, because of its thermal process EDM, because EDM is a thermal process, you will get recast layer, heat affected zone, and all these thermally degraded layers. These layers are maybe oxides, maybe carbides. If you are going to use carbon based dielectric fluids, you will get carbon carbide or the metal carbides. If you are going to use deionized water or some other oxide based, then you will get oxides. Preferably, the persons who are doing research should do on oxide based, so that oxides are soft enough so that it can remove. However, being a constraint in this particular experiments, we have used carbon based dielectric fluids, because of which what will happen? The hardness is much higher, so the finishing ability is low. So, as you can see the percentage change in RA, as you increase extrusion pressure, what is going to happen? We know your radial force to axial force ratio will increase. That means your indentation depth will increase and shearing also will improve. That is why your change in delta RA will be good, and you are going to attain a critical surface roughness, beyond which if you are going to increase the extrusion pressure, there will not be much change in the surface roughness. That is why this particular region or this particular value is called critical surface roughness. Let me write RA. And at the same time, corresponding 3D profiles also you can see. Initially it is 3.54 microns. After finishing, it came to 1.8 microns. Just this is a preliminary study, and if at all you want to go through the main studies, you can go through some of the papers of our group with Sachin Singh. Now, we will move on to the number of abrasive flow finishing cycles. As the number of abrasive flow finishing cycles increases, what will happen? Number of times abrasive particle will shear the surface peaks, because surface peaks in a workpiece is constant. But if you are going to increase number of cycles, what will happen? The new abrasive particles will come because of self deformability as well as better flowability. Assume that the new abrasive particles every time will come, and these abrasive particles will shear. If my number of cycles in one case it is 20, another case is it 30, assume. What will happen if the number of cycles is 20, the abrasive particle may touch 20 times. For example, if it is 30 times, that means that number of times abrasive particles which are involving in shearing action will increase. So, the finishing also improve. At the same time, if you go beyond certain value, what will happen? There also you will get some critical surface roughness value, beyond which if you are going to increase the number of cycles, what will happen? You may not get much change in the surface finish. That is why you have to continue and you have to check. The researcher might have stopped at 25 itself, but it is not so, because you have to go beyond certain level and you have to observe whether it is following the critical roughness. That means that the change in surface roughness is very minimal. That is how the critical roughness can be checked, and corresponding the 2D profiles also provided here. so that you can see in this particular picture. So that the initial RA is 3.63 and final normally if you see RA is 1.47 and 1.42. These are the surface roughness values. However, I am saying that this is a preliminary experimentation only. The main experimentation is already there in the paper, you can go through. And the surface roughness would have been still more better if we would have done these pre-finishing experiments. That means that EDM experiments with oxide based dielectric fluids. Okay. So, because of the constraints or laboratory constraints, and at that time we have done with the carbon based dielectric fluids. Now you can see as the abrasive particle mesh size increases, that means that my particle size is decreasing. This is my particle size, this is my particle size, this is my particle size, like that. What is happening here? Your change in surface roughness is decreasing. That means that you are not going to get much change. That means that even if for that purpose the research says in this particular graph is, if you are going to have a good size of particle, assume that you are going to have 220 mesh size or something, you are going to get a good surface finish 180 and 220, because what is happening there is, if abrasive particle is too small, whenever it comes into contact with the finishing region, because of the radialness, because of the radial force and opposite to radial force and other things, these particles may penetrate inside the medium. That is why if you have a big size particle, it is not too big or something, but if it is 180, 220 or something, what will happen? This will have multiple cutting edges, and these cutting edges try to finish the surface peaks. You can see here the surface roughness is 3.6 and it is improved to 0.37 surface roughness, and you can see the gradual change of the surface. This is the surface recast layer surface. From the recast layer surface, slightly reduced recast layer surface, still there is recast layer surface, and predominant recast layer surfaces are there. Apart from it, most of the recast layer is removed in this process by the abrasive particles. And you can see percentage weight of the abrasive particles. As percentage weight of abrasive particles increases, your change in roughness also increasing. That means that your surface roughness is getting good and good. What is happening here? If your percentage is assume that 35, for a unit area you will have this many number of particles. If you are going to have for 45, what is you are going to have? The number of abrasive particles per unit area will increase. That means that number of abrasive particles per unit area will increase. That means that same surface roughness or same surface peaks will encounter with more number of abrasive particles. Whenever it is increased with more number of abrasive particles, what will happen? The load distribution will decrease. At the same time, smooth finishing can be taken place and good surface roughness can be achieved. That is evident from this particular graph. If you are having a approximately same amount of surface roughness initially, if you do with 0.35, 0.45 and 50, you can see the surface. So, the number of abrasive particles are going to increase. If the number of abrasive particles are going to increase, what will happen? Number of abrasive particles that will hit the same surface roughness. Assume that this is my surface roughness. If one case the abrasive particles are 10, in another case abrasive particles are 20, what will happen? The 20 abrasive particles will take part into the finishing action and the surface roughness obviously will be better. That means surface finish will be better, surface roughness will reduce. Now you can see here the initial surface and final surface, how this is achieved. Till now we have seen how the extrusion pressure, number of cycles, weight percentage of abrasive particles plays a major role. Once you do all these experiments, you get some preliminary idea how much extrusion pressure I have to use, how much number of cycles I have to use, how much abrasive particles concentration we have to use in the medium. That basic knowledge will come then you can do the complete experimentation using design of experiments or full factorial experiments, and you can get with a good surface. That experimentation is carried out, full experimentation using design of experiments is carried out, and the initial surface roughness you can see here of the micro slot wall. Assume that this is my micro slot, we are going to cut this one about this axis and we are going to measure this particular wall surface roughness. Here we are going to find the surface roughness value. Now you can see the initial surface roughness. Initial surface roughness consists of dominating recast layer and the surface is too rough. The surface value is approximately 3.6 micrometers. So you can see predominant surface peaks and valleys. You cannot do much about valleys, but only thing that you can do is you can do the finishing of the surface peaks. At the same time, recast layer will be hard and brittle in nature because it is a carbides. So sometimes delamination of this brittle layers also will takes place and goes along with the medium. Whenever the optimum conditions are used, like pressure is 5 megapascal, that is 50 bar pressure, number of cycles is 30 and percentage abrasives is 50%. For this combination, you can see the surface roughness improvement in terms of RA, it has increased to 0.19 micrometer, that means that 190 nanometers. And you can clearly see the transformation from the recast layer to a approximately parental material. Okay. You can see here the surface transformation by using the polymer assisted abrasive finishing process. These thermal layers, whatever are formed because of the melting and resolidification, are completely disappeared, and you can have the shearing marks of your abrasive particles along the direction of the medium motion. So if you are going to put these two surfaces in a practical application, the recast layer dominating initial surface roughness will enormously reduces its life. At the same time, finished surface will improve the component life. So at the same time, this recast layer, as I said, cracks formation will be there because these are a carbide formation and other thing. Because of this, what will happen is this material will goes off by the action of brittle fracture. But here, if it is finished, that will be good. At the same time, you can also confirm this by using elemental analysis, that is energy dispersive spectroscopy, EDS. You can see here the surface, EDM surface, it is consist of mostly carbides and iron, other things, because of which you can see the surface finish also not good. And as I said, this if you are going to use in the practical application, it is going to fail early. But if you are going to polish the surface and if you take, what will happen, your carbon content is enormously reduced. However, normally speaking, as a metallurgist, normally metallurgist people may not take the carbon content and oxygen content. However, to show the carbon content, because we have used carbon based dielectric fluids in the initial or pre-finishing state, that is why we have shown, and you can clearly see the crater formation. These are the crater formation, that means that melting and evaporation is the mechanism of EDM. In that circumstances, some of the material is stayed back and it is cooled by the dielectric fluid. That is why these craters are formed, and these craters are dominated by the recast layer, and the recast layer is one type of carbide which is a brittle and fracture will also takes place. Whenever you do the polishing action or the finishing action using the polymer assisted abrasive medium, what will happen? You are going to get a very good surface. That polishing also will improve. At the same time, not only mechanically it will give good results, metallurgically also you are going to get a near parental material composition. and you can see the surface finish 3.4 microns. From 3.4 microns to it is increasing to 0.1 micron. This is a two-dimensional profile. So it will improve basically, and the author have also done about the simulation studies. If at all you want to know about simulation studies and experimental comparison and other things, you can go through the paper. And for now I am just comparing this with this, because this is the initial and this is the final experimental graphs or experimental surface roughness values. So it gives the good surface roughness, at the same time good metallurgical properties also. That's how the micro slots can be polished, knee implants can be polished, at the same time surgical stainless steel tubes can be polished. So this particular medium is good for micro applications as well as macro applications. Now we move on to another biomedical devices where we use the polymer assisted abrasive flow finishing process. So now we are moving to the micro holes finishing. Till now, as you have seen in the previous ones, what we have seen is micro slots, surgical tubes and other things, knee implant, macro aspects, as well as one of the micro aspects such as micro slots finishing we have seen. Now we move on to still more smaller size micro aspects, that is called micro holes. These micro holes are most important for many medical applications or medical devices such as coronary stents, which is especially drug eluting coronary stents. As you can see here, the stents that are placed inside the human, this is the stent, one you can see in the heart. There is another stent is also visible. Most of the time these stents are made up of nitinol, and some of the times this also will be made up of biodegradable polymers also. So currently what you are seeing here is a metallic based stents, and this has the core inside as a medicine that you can see. If I take a overview of the stent, some of the portion, if you just check, what is you are seeing here is micro holes. These are the micro holes that are there in a stent, and these micro holes will support the drug that will be coming out. Now you can see here the drug is coming out from the holes. In case, as you have seen in the previous slots also, some of the applications they also use slots for drug eluting applications and other things. If you have a recast layer, heat affected zone and other things where some spheroids are still there on the surface, in that circumstances what will happen, whenever the drug is coming out, what will happen is it will come along with the drug, because the chemical reaction will take place. At the same time the drug is flowing, and the spheroids which are unable to evaporate are remelted by the dielectric fluid and stays there itself, because of which these spheroids are loosely bonded, and these may come out along with the drug and may cause lot of problem to the health. That's why if you don't have proper surface roughness, at the same, if you see the laser surface or if you see the EDM surface, what you normally see is the hole will be very rough. If surface is rough, the biggest problem is the drug eluting may not be proper. At the same time, plus these spheroids which are formed will also exit from the surface. These two will damage the tissues which are there in the heart. Apart from it, what is happening here is that controlled drug release. You can see another concept called controlled drug release will not be there. Assume that 1 ml per 1 hour you require. In that circumstances, if the surface roughness is too high, that means that what will happen? It will obstruct the flow. If it is too low, what will happen? Properly drug will elute from that, so that your tissues or your fat that is there in the heart and other things will dissolve and it will rectify. For that purpose, what you require is you have to make sure that it should be properly finished micro holes is required. This is the motivation of what we are going to see in the upcoming slides. The upcoming slides you may not be seeing drug release and other things, but how to polish or how to finish these micro holes so that the drug will be eluting. As a mechanical engineer, our main purpose is to take care of the mechanical structure. In the mechanical structure of a stent, it is a stent structure and manufacturing of the stent. We don't deal with the chemical and other things. Okay. As a group, if somebody is interested, they can obviously go along with the collaborations and they can do that work also. These are all can be done, or these are all can be polished using abrasive flow finishing process, wherein you have the medium. This particular medium is commercially available by Extrude Hone company, or you can prepare your own medium if you have some polymer technology and other collaborations relevant to this polymer chemistry and other things. Okay, this is the polymer medium. You can see here how the polymer assisted finishing is giving. These are the micro holes. A array of micro holes are drilled using EDM process. There is a array tool is there, and you are going to generate the array of holes on the surface. That is clearly visible in the bottom picture. If you see the surface by just doing a cross section of one of the holes, this is the initial surface and this is the final surface. But how we achieve the final surface and other things? Initial surface, can you see the spheroids? If these spheroids are generated because of improper melting and evaporation, the molten metal that is evaporating is stopped by many other reasons, like one of the reasons is flowing of dielectric fluid, and more amount of metal is melted and some is only evaporated, some is staying back. This all will stay back on the surface. Now through this, whatever the drug is going to elute, assume that this is the surface and it has to come through this surface, the drug. What will happen? This drug will carry these spheroid particles, and at the same time this is metallurgically contaminated. You have seen the surface integrity of any particular surface is most important, because surface roughness along with surface metallurgy is important. Neither surface roughness is good in the initial surface, nor surface metallurgy is good in this particular surface. So completely surface integrity is poor. So our intention is to reduce the surface roughness and to remove these metallurgically destroyed thermal layers. That we are going to do. The first thing, how we have generated using a EDM process, that you can see die sinking EDM. A array of micro holes are generated using a array based tool that is clearly visible here. And second thing is you can generate this one. This generated workpiece is carried or placed in the fixture, and this fixture will be placed in the abrasive flow finishing process. Now your reciprocation of the medium will takes place in abrasive flow finishing process. This is above this you have a medium cylinder, and below this you have a medium cylinder, and this is a piston through which medium will reciprocate. This reciprocating medium will try to finish the micro holes that are generated by EDM process, so that thermal layers which are deteriorated will goes off. Along with that you will get a good surface roughness also. Now we can see the extrusion pressure effect on the micro holes finishing. If you have the 3 megapascal, 4 megapascal and 5 megapascal, the thing is that at low pressures, that means that your axial force and axial velocity, radial force approximately small compared to your 5 megapixel. That means that here 5 megapixel means 50 bar, 40 bar, 30 bar. In terms of, you may see that only it is a difference of 1 megapixel, but in terms of bar it is slightly higher side. That's why your values of FA1, FA2, radial force and other things are approximately small, because of which what will happen, partial indentation and partial axial motion will be there, because of which what will happen, the medium is unable to remove the most of the spheroids that are there in the finishing region. If you increase further, what will happen, the surface roughness has improved and you can see most of the spheroids are clearly removed from the surface. However, any process will have some of the defects. At the same time, this is particularly a preliminary experimentation is carried out, at what pressure the finishing action is going to take place in a better way. So then what we will do, we take the experimental range and we will do the complete experimentation later. Okay. For that purpose, you can refer Sachin Singh as well as Dr. Ravi Shankar, myself, papers for the abrasive flow finishing of micro holes. And if you still further increase, what will happen is, finishing is approximately same, but the thing is that indentations are taking place because of high extrusion pressure and other things. The same thing is reflecting here. The critical surface roughness is achieved here, and beyond which if you are going to increase the extrusion pressure, there may not be a substantial improvement of change in surface roughness. Even though you are going to increase the extrusion pressure, what will happen? Your force ratio will increase. If your force ratio will increase, that means that increment of radial force is increasing, because of which indentation will be predominant. Not only the surface finish will take place, but also it can create the deep scratches. Now we will see with respect to number of cycles. As the number of cycles increases, obviously the surface roughness will improve. That is evident from the graph. And here also it is achieving approximately the critical surface roughness value. Approximately is achieving the critical surface value after 6 number of cycles. So you can see here the surface is predominantly by EDM surface, because the pre-finishing process is EDM. Here also you can see some of the EDM marks as well as some of the finishing marks, but if you go for 10 number of cycles and beyond, what will happen? There won't be much change, but indentation is also taking place here. Some of the materials is removing and indentation also may be taking in, because of which you can see there is a good change, but sufficient amount of change is not there beyond certain value. Now we will see with respect to abrasive particle mesh size. That means that whether you are going to use 220, whether you are going to use 180 or 400, 600 or 1000, like that the values are used. These are the mesh sizes. As you know, the mesh size values increases, the abrasive particle size will decrease. At the same time, percentage delta RA, change in surface roughness is decreasing. That means that roughness value is also decreasing as you are increasing the mesh size. That means that particle size you are going to reduce. If you see in this particular context, here abrasive size is like this, gradually it is decreasing. So like this. If you have bigger abrasive particle, at least in a medium, you have a medium slug, you have a bigger abrasive particle. In that circumstances, what will happen? Some of the edge may in contact with the surface roughness. If you are going to use too small abrasive particles, what will happen is, because of the radial effect, which is it has to indent, it may sometimes push back also. That problem is there because the medium is viscoelastic in nature. That's why proper finishing is not done if you are going to use very high super finished abrasive particles. Whenever you are going to use low viscous abrasive flow finishing medium or low viscous polymer assisted abrasive medium. The same thing you can see hash 1600, hash 180, 400 and other things. If you are using 180, normally you have a good surface roughness, but you at the same time you will have some of the indentations also. But however, indentations are much smaller compared to your other thermal layers. You can see here, this is EDM surface because the EDM recast layer, it is a brittle layer, that is EDM surface. Here also cracks are enormously there. If you are going to increase, what will happen? These cracks are gradually goes off. Cracks due to recast layer of EDM process. These cracks should be removed. That can be only removed if you are going to use bigger sizes abrasive particles. And however, as I said, no, bigger sizes abrasive particle means small size mesh sizes, that is 180 mesh size or 220 mesh size. If you are going to use, what will happen? The finishing action will take place. However, 180 may cause some of the indentation because of its bigger sizes. Before abrasive flow finishing and after abrasive flow finishing, if you know what is the extrusion pressure that you have to apply from the preliminary experimentation, number of cycles and abrasive mesh size, once you do all these things, then you have to do from that ranges you will get. Assume that I get a extrusion pressure some range, number of cycles some range, then abrasive particle size some range, then you do complete experimentation. After complete experimentation, that experimentation is not shown because of the time constraint. If I start teaching that, it will take lot of time. So the optimum conditions ranges can be get. Optimum conditions will be known from the preliminary experimentation, followed by you do the complete experimentation using design of experiments or full factorial and other things. Then you will get a good surface, that is what here shown. So after full experimentations we have shown here. If at all you want to know about full experimentation, you can go through the paper of micro holes finishing. You can see the initial surface 2D and 3D surface and the final surface. Normally 1.47 is the initial surface and 0.13 is the final surface. So EDM surface is removed enormously. At the same time, you can also see some of the scratch marks by the abrasive particles. These will show that it is removed the surface that is randomly generated by the EDM process, and later on the finishing is taken place. Not only that, we have to cross check the metallurgical aspects also. If you can say that oxide layers are there or carbide layers are there, then it will be a problem. That is why the metallurgical aspects before finishing and after finishing we have seen, and the carbon content, normally this shows that carbides are high in the initial stated, and however you should not take the carbon in a EDAX analysis, but if there is a carbon change, what we assumed is that there may be iron carbides forming in the workpiece. So you can see here the carbon percentage is less. At the same time, what as a mechanical engineer, what you can infer from the surface morphology is a smooth surface is achieved by abrasive flow finishing medium, which is having a polymer that is assisting the abrasive particle. These abrasive particles which gets assistance from the polymer will try to shear off this recast layer and the spheroids that are formed on the workpiece surfaces. Now medium special properties. This medium can finish the bigger holes, this medium can finish the smaller holes also, because it is temperature sensitive in nature, and this particular graph, if you have seen in the abrasive flow finishing process, that will be well explained there. And at the same time, what I want to say is that this medium is temperature sensitive medium, and if you can use this medium for bigger holes, this one, and if you can have a temperature controller on medium cylinders, you can manipulate the temperature. Same medium with temperature effect you can utilize for micro holes also. So the applications, some of the applications, not only biomedical applications, you can also use for automobile, that is fuel injector nozzles, at the same time deburring, radiusing and finishing also you can see. These are all explained in the abrasive flow finishing process itself. Still, what I want to show here is that you can do the polishing of the micro holes in automobile industry also, and some of the implants that are finished across the globe you can see here. This is the knee implant which you have seen, drug eluting stents. These are the pictures are taken. However, finishing process is under the preliminary conditions. At the same time, acetabular socket head, initial surface and final surface. Acetabular socket head is obviously required for the medical application. At the same time, this acetabular socket also should be finished, because so that both will have proper motion with respect to the hip. If you have a proper surface finish of the acetabular head and acetabular socket, then your hip joint will be in good condition, so that the life of the hip joint will be very good. And hip joint itself, the stem itself also can be polished using abrasive flow finishing process. And in abrasive flow finishing process, people regularly uses the polymer rheological abrasive medium, and this is another acknowledgement. This is done in collaboration with CMTI Bangalore. Extrude Hone is a company that finishes extensively into abrasive flow finishing, where they develop a very sophisticated the polymer rheological abrasive medium. Thank you for your kind attention for this particular class.